The rest of section 3.1 deals with probabilities. Probabilities you're familiar with. I wanted to just mention that probabilities can be written either as a fraction, decimal, or percent. Now, when you're working with probabilities, there is a round-off rule for decimals. So the round-off rule is to go to 3 decimal places. So when you convert that into a percent, it's going to go to the nearest tenth. So there are 3 types of probability that we need to learn about. The first type is going to be what we call classical or theoretical probability. In classical probability, each outcome in the sample space is equally likely to occur. So think about rolling a number cube or drawing a card. Each of the outcomes of rolling a 1 or a 2 or a 3 or a 4 or a 5 or a 6, each one would be equally likely to occur. The way that we talk about the probability of an event is we use a capital P and then a capital E, but that E is going to be whatever the event is. So this symbol is the probability of event E. Now, what I will put in there is like rolling a 2, so probability of rolling a 2 instead of an E there, unless I tell you E is rolling a 2, and then I'll say PE. You'll see in a minute. So the probability of event E is going to be the number of outcomes in event E divided by the total number of outcomes in the sample space. So let's look at this example for finding classical probabilities. So event A is defined as rolling a 3. So the probability of event A happening is going to be the number of outcomes in event A. Well, event A is rolling a 3. So if you're rolling a 6-sided die, remember that the sample space for that would be 1, 2, 3, 4, 5, and 6. So there's only one outcome in that event. So that will be 1 divided by the total number of outcomes in the sample space, which would be the 6 numbers on the die. So the probability of event A is 1/6. Event B is rolling a 7. So the probability of event B would be the number of outcomes in which we roll a 7 divided by the total number of outcomes in the sample space. So our sample space was 1, 2, 3, 4, 5, and 6. So there are 0 7s in there divided by 6 in our sample space. So the probability of event B is 0. Event C is the probability of rolling a number less than 5. So remember that C would be considered something that's not a simple event. Rolling a 3 is a simple event because there's only one outcome that pertains to that event. Rolling a number less than 5 is not a simple event because if we roll less than 5, then we could roll a 1, a 2, a 3, or a 4. So the probability of event C, which we could write the probability that we roll less than 5, there would be 4 outcomes in that event. still out of the 6 in the sample space. So we would simplify that and make it 2/3. Now, if we were making these into decimals and percents, then we would divide 2 by 3. So 2 divided by 3, we know it gives us 0.6 repeating. But based on our round off rule, we would go to 3 decimal places. So that would be 0.667. And if we made that into a percent, it would then be 66.7%. So when we got that probability of 0, I kind of want to write somewhere down at the bottom what a probability of 0 means. So if you can go down here, a probability of 0 means it is impossible. So that event is impossible to happen. We cannot roll a 7 on a 6-sided number cube. Okay, let's look at these. Try it yourselves. Here we have a listing of the standard deck of playing cards. It's going to be handy for you to have that in your notes because there will be lots of problems that use playing cards, and it's something that we're not as familiar with today in society as we used to be when we would play cards more frequently, I guess. So when you have problems about cards, I want you to kind of remember that the ace, queen, king, and jack are the ones that are called the face cards. And then these are suits. You have hearts, diamonds, spades, and clubs. So keep that handy somewhere in your notes. So we're going to figure out these probabilities. The probability for event D, which is selecting the 9 of clubs. So the probability for event D, selecting the 9 of clubs would be a simple event because as you can see in here, there's only one 9 of clubs. So the number of outcomes in that event is 1 over the number of outcomes in the sample space, which is 52 because there are 4 suits and 13 cards in each suit. So 1 out of 52. Event E is selecting a heart. So the probability of event E would be hearts. So here we have all of these hearts. There are 13 of them. So 13 events in the outcomes in the event of selecting heart over 52 in the sample space, which simplifies down to 1/4. So this one is not a simple event because 13 outcomes were relevant to it. And then event F, which is selecting a diamond, heart, club, or spade. Well, that would be all of these cards here. So there are 52 outcomes that pertain to that event and 52 outcomes in the sample space. So when we simplify that, we get a probability of 1. So let's add that onto our information down here. A probability of 1 means it is certain to occur. So if I select a card, I am 100% certain that it will be a diamond, a heart, a club, or a spade. The second type of probability that we need to talk about is called empirical or statistical probability. And this is probability that is based on observations that are obtained from probability experiments. So in this case, we actually have data to look at. We're not just theorizing about, how many 2s there are in a deck of cards. We actually have some data. So in this case, the formula is going to be that the probability of event E is equal to the frequency of event E. In other words, how many times event E actually happened divided by the total frequency. So we have symbols that we've used in previous chapters. The frequency of event E is going to be F, and then the total frequency will be the number of events in the sample space. So we've used the letter N for that. So the probability of event E is frequency divided by sample size. Here is an example with empirical probabilities. A company is conducting an online survey of randomly selected individuals to determine how often they recycle. So far, 2,451 people have been surveyed. The frequency distribution shows the results. What is the probability that the next person surveyed always recycles? So we're looking for the probability the next person surveyed always recycles. So the probability of always recycling, that's our event. Our event is that they always recycle, would be the frequency of that event. So the frequency of always recycling, which is 1,054, divided by the total frequency, which is down here at 2,451. When I divide those, I get that probability is about 0.430, which would be 43.0%. So let's do this. Try it yourself. An insurance company determines that in every 100 claims, 4 are fraudulent. What is the probability that the next claim the company processes will be fraudulent? So probability that it is fraudulent will be the frequency of a fraudulent claim divided by the total frequency. So it says in every 100 claims, 4 are fraudulent. So that will be 4 in 100, which is 1 in 25. When you divide that out, you get 0.04, which is going to be 4%. Okay, let's talk about something called the law of large numbers. The law of large numbers says that as an experiment is repeated over and over, what happens is that the empirical probability or the statistical probability, sometimes it's been called the experimental probability, approaches the theoretical probability. So if I were to roll a dice 10 times, more than likely I would not just get a 1 1/6 of the time, and a 2 1/6 of the time, and a 3 1/6 of the time. But if I were to roll that number cube 1,000,000 times, then the empirical probability, the experimental probability, would start to resemble the value for the theoretical probability. Okay, some more empirical probability for you here. A company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. The frequency distribution at the right shows the results. What is the probability that the next user surveyed is 23 to 35 years old? So we would want the frequency of that event. So the frequency of somebody being 33 to 35. 23 to 35. 23 to 35, the frequency is 312 divided by the total frequency, which is 975. So that is 312 over 975. I'm just going to leave that as a fraction. And then on this problem, find the probability that the next user surveyed is 36 to 49 years old. So probability 36 to 49 years old. Again, so that would be the frequency of the event of being 36 to 49, which is 254, divided by the total frequency, which was still 975. But what if I asked you a different question? What if I asked you an off-the-grid question? What is the probability that the next person I choose is between 36 and 65 years old? So I need the frequency of that event of being 36 to 65. So 36 to 65, that frequency would be 254 plus 195, and the total frequency is still 975. So that probability would be 449 out of 975. So this first probability was a simple event. This second probability was a simple event. And the third probability was not a simple event because more than one outcome was relevant to the event of being 36 to 65. The third type of probability that we're going to talk about is subjective probability. Subjective probability is not based on theoretical, like the dice has 6 sides. It's not based on experimental, like rolling the dice a bajillion times. It results from intuition, educated guess, and estimates. So some examples of this would be like when the doctor predicts a 70% chance of full recovery. That's going to be based on his or her experience with similar injuries, but also based on observations of your injury and maybe how you've recovered from things in the past, and just kind of making an educated guess or using intuition. So we're going to kind of practice identifying if something is classical, empirical, or subjective. So the probability that you will get an A on your next test is 0.9 or 90%. There's a 90% probability that you're going to get an A on your next test. Number 2 is the probability that a voter chosen at random will be younger than 35 years old is 0.3. And the probability of winning a 1,000 ticket raffle with one ticket is 1 in 1,000. So probability of getting an A on your next test is 0.9. I mean, that's not theoretical because there's 5 grades and that would be like 1 in 5. So it's not that. It's not going to be empirical because it's not based on having taken that test 1,000 times. So this is going to be subjective. It is based on your past history and making an educated guess or estimate based on your experience. The probability that a voter chosen at random will be younger than 35 years old is 0.3. So this one is going to be empirical because it's going to be based on data about all of the ages of all the voters. And then the probability of winning a raffle, if you have one ticket out of 1,000 that are in there, is theoretical because each ticket has an equally likely chance of being drawn. So let's go on, try it yourself. Based on previous counts, the probability of a salmon successfully passing through a dam on the Columbia River is 0.85. Is this a statement an example of classical, empirical, or subjective? So it says right here it's based on previous counts. So that's not going to be theoretical or subjective. That is going to be empirical because it's based on data that already occurred. Okay, We're going to talk a bit, we're sort of shifting gears to talk about complementary events. Complementary events. So let's say that this box here is the entirety of a sample space. So all of the possible outcomes are in this sample space. Then within that sample space, I'm going to have some event that is E. I could figure out the probability of event E. So what I want to, when I talk about the complement of event E, the complement of event E is all of the things that are not E. So anything outside of event E would be its complement, and we call that E prime. So for an event E, its complement is E prime, and we say that E prime, just as a reminder, E prime. So as you can see in this sample space, E and E prime, which is everything outside of E, make up all of the outcomes in that sample space. So for any event, E and E prime make up all of the outcomes in the sample space. Since all of the outcomes in a sample space would give us a probability of 1 if I added up all their probabilities, what we can say is that the probability of event E plus the probability of its complement, E prime, the probability of this plus the probability of that is going to equal 1 because that's going to be all of the outcomes in that sample space. So let's briefly look at quick examples of this happening. If event E is that I roll a 3 or a 4, then the probability of event E would be the number of outcomes in event E, which was 2, divided by the total number of outcomes in the sample space, which is 6. So the probability of event E is 1/3. Then what would E prime be? E prime would be all of the other outcomes. So E prime would be not rolling a 3 or a 4, or rolling a 1, 2, 5, or 6. So the probability of E prime would be the number of events in E prime, which is 1, 2, 3, 4, number of outcomes in that event, divided by the total number of outcomes in the sample space, which is 6. So the probability of E prime is 2/3. And if you notice, if I add up the probability of E to the probability of E prime, 2/3 plus 1/3, I get 1. So we can use this to our advantage. If we know the probability of an event happening, we can find the probability of its complement. But likewise, if we know the probability of the complement, then we can use it to find the probability of an outcome. So we're going to start here, finding the probability of the complement of an event. So we're using the frequency distribution in example 7 to find the probability of randomly selecting a social networking site user who is not 25 to 35 years old. So we're going to be needing this little data table here from example 7 to answer this question. So what is our event that we're wanting to find the probability? Our event E is picking a user who is not 23 to 35 years old. So then what would E prime be? E prime would be everything except being not 23 to 35 years old. So in other words, E prime is that the person is 23 to 35 years old. Since I know the probability of E plus the probability of E prime equals 1, in order for me to find the probability of E, I can add probability of E to the probability of E prime, which I know is 312 over 975, and that's going to equal 1. So then the probability of E is going to be 1 minus 312 over 975, which is 663 out of 975. 663 out of 975 is 0.68, which would be 17/25. Okay, let's do just the rest of the examples on this page, and then we'll be done with this section. Using the frequency distribution in example 7, find the probability of randomly selecting a user who is not 18 to 22 years old. So in this case, E is not 18 to 22. So E prime would be that the person is 18 to 22. So the probability of E plus the probability of being 18 to 22, which is, if you look at your chart, 156 out of 975 equals 1. So the probability of our event would be 1 minus 156 over 975, which is 819 over 975, or 0.84, which is 21/25. Okay, this little spinner goes with this tree diagram and goes with this example 10. A probability experiment consists of tossing a coin and spinning the spinner shown up here. So that spinner has 8 equally sized sections. The spinner is equally likely to land on each number. Use a tree diagram to find the probability of each event. So here's our tree diagram. The first thing to happen is to toss a coin. The second thing is to spin the spinner. And so this is my sample space out here. H1, H2, H3, H4, all the way through T8. For event A, they want the probability that you will toss a tail and spin an odd number. So tossing a tail, so probability of A, we are tossing a tail and then spinning an odd number. So that is not going to be a simple event, because tossing a tail and spinning an odd number would be tails in 1, tails in 3, tails in 5, tails in 7. So we'd have 4 outcomes in that event out of the 16 outcomes in our sample space. So that probability would be 1/4. What about the probability of tossing a head or spinning a number greater than 3? Okay, this one's going to be more complicated, because what we're doing here is we're either tossing a head or spinning a number greater than 3. So tossing a head would be all of these. So there's 8 of those that are happening. Or we could also be spinning a number greater than 3, so that would be these as well. Now we've already counted these in the 8 from tossing heads up here. So we have to also include these 5 down here. So there are 8 in this part of our event and 5 in this part. So the probability for event B would be 8 plus 5 out of 16, which is 13/16. We're going to call this event C. Event C is going to be tossing a tail and spinning a number less than 6. So this word "and" means that what we're looking for has to be a tail, and it also has to be a number less than 6. So a tail that's also less than 6 would be these 5. So the probability of event C would be 5 out of 16. Okay, example 11. Example 11, using the fundamental counting principle. Your college ID consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? So the first thing we want to know is how many are in the sample space. So the sample space is going to consist of all of the possible ID numbers that I can create. So in my sample space, it's going to have, I'm going to have to figure that out using the fundamental counting principle. There are 8 digits. And since my numbers can be repeated using the digits 0 through 9, each of those 8 decisions to be made has 10 possible choices. So my sample space is going to have 10 to the 8th, or 100 million possible outcomes. So when we're looking at probability, remember, probability is going to be the number of outcomes in our event divided by the total number of outcomes in the sample space. Well, the event is getting your college identification number. So the probability of getting your ID number, how many events are there in that? How many outcomes are there in the event of getting your ID number? There's only one because you get one ID number. And how many in our sample space would be 100 million. So the probability of randomly generating your specific ID number is 1 in 100 million. Okay, now your college identification number consists of 9 digits. The first 2 digits of each number will be the last 2 digits of the year you are scheduled to graduate. So let's see. Now we got to figure out how many are in my sample space. Let's see, I've got 9 digits. 1, 2, 3, 4, 6, 7, 8, 9. Okay, the first 2 digits are going to be the year I graduate. Well, I'm going to assume I know the year I graduate. So since I know the year that I'm going to graduate, there's only one choice for each of those digits. Then all the other places have the digits 0 through 9, and they can repeat. So those are all going to have 10 choices. So the number of possible outcomes is going to be 1 squared times 10 to the 7th, which will be 10 million possible outcomes, or 10 million possible IDs. So now the probability of getting my ID number there's still only one way to get my ID number, but now there are 10 million ways, or 10 million possible IDs in the sample space.